Yeah, the attendance poll is 428. I see that the classroom is incredibly empty, so if this continues from the next class, I will actually bring a piece of paper and have you guys sign. Everybody who signed up for the in-person class, section A, I will expect you in the classroom from the next class. And if you're not here, if you don't sign my piece of paper, you might as well not attend on Zoom. I'm going to mark you absent because this is not acceptable. Yeah.
How do you do the 428 again, sir? I'm not really sure.
So Piazza poll 428, right? Yeah, it's up. All right. So please settle down. Shut your laptops. And this is incredibly, embarrassing. I have like 30 people in class, and the enrollment is 330. So 90% of you are basically absent. You're pretending to be on Zoom. I know you're not there. Lady, can you shut your laptop, please? I do not want you guys opening your laptop. Everybody, come up front. Come up front, please. I want to leave the back of the class empty so everybody sees exactly how embarrassingly bad and idiotic this class is. Come on up front. Those at the back, come on up front. You there, come on up front. Come on up. Yes, all of you. I want the back seats empty. Can you guys come up front, please? There are seats in front. I mean, it's bad enough that I'm late. You guys make me feel even worse by not being in class. Yes.
Yeah.
You're just not interested. Okay, guys. All right, let's start. Those in the back, please come up front. We're going to start today here. We're continuing with our business on optimizing neural networks. We have 3 full rows empty in the back of the class. That's bad. So here's what we've seen so far. Neural networks are universal approximators, but we must train them to approximate any function. And the way we train them is by minimizing a loss on a training set, which we do through empirical risk minimization. We use variance of gradient descent to do so. And the gradient of the error with respect to the network is computed through backpropagation. Backpropagation doesn't do the training. Backpropagation computes the derivative, right? So, and here's how we set up the problem. We defined a loss, which was the average divergence over the training set. And the derivatives are basically the derivatives of the loss, which is the average of the derivatives of the divergences for the individual training instances. That's the term we wanted to compute. And that's what backpropagation computed. And so here's what the neural network looks like. Each layer, the k-1th layer, generates the vector yk minus 1, which is transformed using the weights for the kth layer and the bias to give you the zk. So zk is dependent on yk, and then zk is the affine term, and then zk influences yk, which is the output of the kth layer. And then the output of every layer eventually influences the divergence. So if I just place the derivatives for the variables on the edges, what is the derivative of zk with respect to yk minus 1, given the affine relationship? Anybody? Yeah. Actually, no, so not you. You answered too many questions. Somebody from the back. So what's the derivative of zk with respect to yk minus 1?
WK?
WK, the weights, right? So, okay. And then what is the derivative of yk with respect to zk? Yeah. That is just going to be the Jacobian. That's what we have on top of the edges, right? And so when we were computing our derivatives going backwards through the chain of influences, how exactly did we, what is the rule we applied at each point? Chain rule. And so how did the chain rule work? Anybody? Yes. So as you keep going backwards, we keep right multiplying the derivatives. So the derivative of the divergence with respect to zk is going to be the derivative of the divergence with respect to yk times the derivative of yk with respect to zk. We just write multiply. That's the Jacobian. And then the derivative of the divergence with respect to yk minus 1 was simply the derivative of the divergence with respect to zk times the derivative of zk with respect to yk minus 1, which is just the weight matrix. And so you can see that the backpropagation rules are really very trivial when written in vector format, right? And furthermore, the derivative for the bias is simply the derivative for z. And we saw that the derivative for the weights at any edge comprises the product of the input to the edge and the derivative at the output of the edge. So if you have yk minus 1 influencing zk through wk, then the derivative of the divergence with respect to wk was yk minus 1 times the derivative of the divergence with respect to zk. So this simple set of rules gave us the entire backpropagation algorithm. Nothing very complicated. If you were to write it using vector formalisms, that's all you would write, okay? And so here is the entire backpropagation rule. As you went through the training instances, each training instance is propagated forward through the network, and you get the output and all the intermediate variables. And then you just perform backpropagation where you repeatedly just compute the derivatives with respect to the network parameters and update the overall loss derivative, which you can use within gradient descent, right? So here's the first pole, or the 0th pole. I need that. Once. I need the Pokemon. Oh, yeah. All right. Awesome. Okay, I'm going to begin calling out names. Who's Golduck? Is Golduck here or on Zoom? Golduck's absent.
Yeah, that's me.
Okay. All right, Golduck. Is that first statement, which is the answer to this poll? Come on, guys, okay?
The third one?
All right. So who's B-drill? Who is B-drill? B-drill is absent, okay? And who is Magby, M-A-G-B-Y? Who's Magby? Magby is also absent, okay? And who's Swellow, S-W-E-L-L-O-W? Who's Swellow? Hmm? That's you, okay. Which one's the answer?
The first one.
The first one. Does everybody agree that the first one is the answer? Because it must, come on guys, I've written it down here for you. It cannot be easier than that, right? If you're not seeing what's on the board and answering my question, you guys are not paying attention to me, the board, the slides, or anything. So that's not right. Shut your laptops. Okay. And so let's continue, right? Anybody seen this movie? So we're going to look at a few things. We are 10 minutes late, but hopefully we'll catch up. I'll speak very fast. You played out at 1.25, so there'll be 1.5. Anyways, does backpropagation always work? Meaning, I'm speaking of backpropagation, but really, if I use gradient descent to compute my optimum, does that always work? That's what they mean. What are the convergence, how does the convergence of gradient descent work? What are the rates? What are restrictions? Second derivatives, how do they influence things? We'll look at some of these in the next two classes, right? Okay. So the lady there, can you shut your laptop? You there? Yeah. So is that your laptop that you're looking at, or you're taking notes? Yeah. Okay, fine. All right. So is backprop always right? Meaning, we are speaking of historically when people have used the term backprop to actually talk about gradient descent using backprop. So this is really, a slight abuse of terminology, but I'm going to use it nonetheless, right? So does it always give the right answer? Now, we've already seen this in the a couple of classes ago. The error that you want to minimize is actually the misclassification rate. But we saw that the misclassification rate is not a good objective. And why was this the case? Why was misclassification rate not a good objective? Anybody? Yes? Go ahead, Pat.
Small movement in the rate would not tell us which direction.
Their derivative is 0, or basically it has no derivative. It doesn't tell you which way to move your parameters. So we replaced it by this proxy, which was not actually the misclassification rate, but gave us the cumulative distance between the target output and the output of the network. And is this proxy perfect? Would minimizing this proxy minimize the misclassification rate? Yes or no? No, right? And so we saw why, right? In classification problems, the classification error is non-differentiable. So the divergence function we minimize is only a proxy for the error. And minimizing the divergence may not minimize classification error. Let's see a very nice example. This is by Brady, Raghavan, and Sloney back in 1989. So here's an example. I have the red class and the blue class. All of those dots in red are instances from the red class. The dots in blue are the instances from the blue class. Assume that there are like millions of instances from both classes. Now, if I were to use the perceptron learning rule, would it find a boundary? Right? Are the classes linearly separable? Yes. So the perceptron rule would find the boundary. What about if I just use this proxy, right? Assume I'm using a quadratic proxy, right? And use gradient descent. Would it find the boundary? Over here. Clearly, right? It's a very nice, separable classes. So backprop-based gradient descent and the perceptron algorithm, both of them would find decision boundaries, perfect decision boundaries. Now, add one spoiler. There's just this one red dot. Now, what is the guarantee we had with the perceptron rule? That if the classes were linearly separable, it would always find the boundary. So the perceptron rule is going to find the boundary, right? But what about if I use the proxy and perform gradient descent? What would happen? Because the other dots are so many in number, this one thing is not going to contribute very much to the overall loss. And so that one might maybe just change a little bit, right? Now, if I move the spoiler from here to there, the perceptron rule is still going to find the boundary. What would gradient descent do? It's just going to perturb the solution a little bit, yes?
So kind of settle at like a local optimum for classification as opposed to like a global optimum, which is like perfectly linearly separating the classes.
Yeah, so long as I have any kind, and if I let the weights go to infinity, then there's no distinction between the two because infinite weights can give you a vertical wall, right? But if I restrict the weights, even with a finite length, if I say the length of the weight vector is 1, there is a solution, but gradient descent will not find it, right? So, or if I move the dot here, then the perceptron rule is going to find the boundary. The gradient descent rule is not going to find it, right? So, and so on, right? Every time I move the dot, I have one spoiler, and just moving it around can make my perceptron solution swing wildly. The gradient descent solution will not. Yes?
So, I don't quite follow that. Are you saying the gradient descent solution can never find it, or that it's going to be quite sensitive to where you're starting?
No, it just says it will not find it. Think about this, right? So if I have this blue collection of blues, I have a collection of reds out here, and let's say I have 10 raised to 90 of these guys and 10 raised to 90 of these guys, right? Then if I just add one more dot over here, just one, will it change the overall loss a huge bit? No. So will the solution change? That's the point, right? Whereas the perceptron rule is going to swing around. And so the perceptron may change greatly upon adding just a new training instance, which means it fits the training data really well. This is what is called, this is what we mean when we say it has low bias. If there's a solution, it's going to find it. But that means it swings a lot. Moving a single point can change your solution completely. It has very high variance. On the other hand, the backprop-based mechanism, gradient descent, prefers consistency over accuracy. So it introduces biases. It's going to ignore these wild things. But contrary-wise, it's not going to swing a lot from instance to instance. So yeah.
I remember in regression, for example, sometimes one point can change the regression line number if it is outlier point. Like that inverse.
That's basically what is happening. I mean, so again, it depends. So it depends on your loss function, but the general setting is just this, right? Yeah.
So is the reason why they call like perceptron bias? No, the reason why they call say perceptron doesn't have bias is it because like if it's zero, while like the reason why like backprop is biased is because like it has like this sort of like boundary that it wants to conform to.
So backprop wants to conform to the majority. The perceptron rule is going to conform to A, try to find whatever boundary you can find, right? So which is why, so which of these two behaviors would you prefer? Which one would you prefer?
The one that backprop gives us.
The one that backprop gives us, because you don't want to be sensitive to even, to the movement of one little data point. And so it's a low variance estimator at the potential cost of bias. This is not a bug, it's a feature. Okay? And now that's for a single perceptron. But then if I have a neural network which captures more complex boundaries, the same story holds. I can have a bunch of data this way, and the red line could be the boundary that the neural network captures. Adding one data point over there is not going to swing the whole boundary out and change my entire solution. It's going to maybe move up just a little bit. And so backpropagation will often not find a separating solution, even though the solution is within the class of functions learnable by the network, right? So when I added that one dot, that boundary is representable by a weight, which a network can capture, but it won't get it, right? And this is because the separating solution is not a feasible optimum for the loss function, because we're using a proxy, not the classification error itself. And so one resulting benefit is that a backprop trained neural network classifier has lower variance than an optimal classifier for the training data. Okay? Questions? Yes?
How do we deal with these small edge cases in real life? Like they can.
You throw them in, and it's going to learn to not let them influence the overall solution very much.
But like, what if that misclassification is the cause of the light event?
Well, you're going to die. Right? So, okay, here's your problem. This is an easy one. I'm only going to give you 15 seconds. Another 15 seconds to call out all the apps and Pokemon names. So who's Magneton? Okay, answer please. Thank you, right? Minimizing the differentiable loss function will not necessarily minimize the classification error. This is not a bug. It's a feature, right? So now, moving on. In all of this, I've assumed that there's some kind of an optimum for the loss that I can find. But what does the loss surface actually look like? The loss surface, doesn't look like a nice bowl. It's going to look ugly, something like this. And so that's going to influence the solutions that you find. And people have spent a lot of time trying to understand what the loss surface looks like. There are many hypotheses about it, but here are some generally accepted hypotheses, which is that in a loss function, saddle points. Now, how did we define a saddle point? Anybody? Yeah. It's a saddle point which is a flat region, which is not necessarily a minimum. It's maybe a minimum in one direction and a maximum in the other. So saddle points are far more common than local minima for large networks. Now, none of this holds for small networks. So small networks, you're in deep trouble, right? But as you make the networks larger, these things tend to hold. Also, although you have many local minima, it turns out that all of these local minima are kind of equivalent. It doesn't matter in which of these you land, you're still going to get a reasonable solution. So, but if you're using gradient descent, they like to get stuck in points like these, which tends to be an issue. We'll see more of this in the next class. So the story so far, neural networks can be trained via gradient descent. Backprop can be used to derive the derivatives of the loss. Gradient descent is not guaranteed to find the true solution, even if it exists, it's unique, and lies within the capacity of the network to model. And this is because the optimum for the loss function may not be the true solution, and this is because our loss function is a proxy for what we really want to minimize, and minimizing the proxy has no guarantees, right? For large functions, the loss function may have a large number of unpleasant saddle points or local minima, and backpropagation gradient descent basically may just find these. Now, in all of this, I have made a simple assumption that the training arrives at a local minimum, but will it really do so, right? And if it does so, how long does it take? It turns out an MLP is a really ugly function. So we're going to use something called the streetlight effect. How many of you are familiar with this term? Yes?
Oh, you want?
You had a question?
No, I was just saying.
Okay, so the streetlight effect, you must have all heard this joke. Some guy loses his key in a bar, and then the policeman finds him searching for the key at a a street light outside the bar. And he asks him why. He says, well, it's dark inside the bar. I'm not going to find anything there. I might as well see where I can, look where I can see stuff. Now, it may seem illogical, but you know what? If he has dropped his key out near the electric pole, he might find it. He's not going to find it in the bar. So we're going to do this. We're going to analyze what we can analyze, and we're going to sort of try to transfer what we have understood from this analysis to more realistic situations. And what is it we can analyze? We know how to analyze convex functions. Does anybody know what a convex function is? Yes, what's a convex function?
If you draw any 2 points and join them, they won't intersect the line.
So a convex function is a function of this kind, where if I take, it has this kind of property, and if I take any 2 points on it and then draw a line, every point on the line is going to be above the function. It doesn't matter where I take these 2 points, the point is going to be above the function. Can anybody give me an example of a convex function? Yeah. Y equals x squared, a quadratic, and downward quadratic, right? It's always now, and typically we also speak of convex sets. What's a convex set, anybody? How do you understand a convex set?
Set of all circles.
A convex set is a set of points where if I take any 2 points inside the set and connect them up, all points on the line stay within the set. So here's an example of a function that's not convex. I took 2 points above the curve, I connected them, the line goes out below the curve, right? Here's a set that's not convex. I took 2 points in the set, connected them up, part of the line fell outside the set. So generally when we speak of convex optimization, we're speaking of the first case where we are trying to optimize convex functions within convex sets. So we'll use that as our base case. And it turns out that the best possible convex function for analysis is the quadratic function. So that's what we're going to be talking about. Now, when I'm speaking of gradient descent, I want gradient descent to converge. So Noah, what do I mean by convergence in this case?
You want it to, essentially, you want it to be optimized to reach the minimum.
So when I speak of convergence, I basically wanted to take steps and eventually arrive at the fixed point, 0. Now, your gradient descent doesn't necessarily converge. It can end up getting close to the minimum, but instead of going there, it can keep bouncing around, right? Or it can even diverge. It can, instead of getting closer and closer, it can keep getting farther and farther away. So let's look at situations where these different things can happen. And for this, I'm going to analyze, is there the eraser here? Yeah. I'm going to analyze a very nice convex function, which is the quadratic. Now, in some sense, the quadratic function is the ideal convex function. And that is just the right amount of steep far away and just the right amount of shallow at the minimum. Okay. So can somebody give me the formula for a quadratic function that is a downward bowl? Anyone? So can you say that aloud, Damugar?
Y equals x squared.
Y, a generic formula. Come on, guys, somebody tell me. So, okay, y equals ax squared plus bx plus c, right? And so is this an upward? Oh, I'm going to make one modification. I'm going to put a half over here, because when we take derivatives, the 2 will sort of cancel the half out, right? Now, is this an upward facing bowl? Is it convex or is it downward facing? It depends on A, right? What kind of A makes it upward facing? A must be positive. So A has to be positive, okay? And this is going to give you a bowl of this kind. Now, where is the minimum of this bowl? Anybody? How would you find the minimum? Yeah.
You complete the square. And, you complete the square and then you find like the negative B and then C.
So you complete the square, yeah.
Yeah.
So I can just take the derivative and equate it to 0, can I not? And so that's, if I take the derivative and equate it to 0, I say x plus b equals 0, x equals minus b over a. That's where the minimum is. This is easy, right? That's one way of doing it. But then, if you're really, really fond of gradient descent, then how would you solve this problem using gradient descent? Eleanor. Somebody else? I just use the gradient descent rule, right? I can start off with an initial guess. I can say x hat 0, or x hat k is my current estimate. And so I can say x hat k plus 1 equals x hat k minus eta dy over dx computed at x hat k. So this is your standard gradient descent solution, right? Now, how would this behave? If I start off at some point and say this is my guess, you're going to keep walking against the derivative till you get to the minimum, right? So is there a solution where I can get to the minimum in a single step? What would that be, Muhammad?
Just need a bigger step. Just need a bigger.
What is the size of the step? Yeah.
The difference between the current step and the.
There's actually a very nice formula for this, okay? So let's keep this. Okay, I'm going to leave this on top because I want you guys to see that, and I'm going to write over here. So how many of you are familiar with Taylor series? Okay, so that's what your gradient descent would be, right? Wk plus 1 equals Wk minus eta of the derivative. Now, how many of you are familiar with Taylor series? Anybody? Come on, you guys. Mugur, I know you know, right? So what is the Taylor series expansion of a function? So a Taylor series expansion of a function is a polynomial approximation to the function. I have some function f of x, and I want to write this as a plus a0 plus a1 x plus a2 x squared plus a3 x cubed, and so on, with a specific property, right? So if I take I will take an approximation at some point xk. I choose my point, and then if I look at the first derivative of this approximation at xk, it will be exactly the same as the first derivative of f of xk itself. The second derivative is going to be exactly the same as the second derivative of f of xk. The third is going to be the same as, meaning all the derivatives of the term on the right, sequence on the right, are going to be the same as the derivatives of the function itself at a very specific point. So then this is the point around which you're taking the approximation. And so let's look at the first derivative. The first derivative is just going to be f1, right? So I would say f of x. What is the zeroth derivative of the term to the right? That's just a0, right? So if a0 is the same as this, if the zeroth derivative of the two guys is the same, then I want to say f of xk, right? So a0 must be f of xk. What is the first derivative of the term to the right? A1, right? And the a1 plus all of these other guys, don't forget, you have all of these other guys. They're also going to be contributing to the derivatives. So what I would say is f of f prime of xk, and then it's going to be x minus xk. So if I truncate the sequence after just one term, then this is good. It's going to be just this one. And then you can see that at xk, this guy will cancel out. And so the value is correct. But at xk, if I take the first derivative, this doesn't have a derivative. So that's only going to, this will go away. That's going to retain f prime, right? If I take this, if I want to have a second derivative approximation, that's going to be xk squared. You can see this again. So if you plug in x equals xk over here, you're going to get f of xk. If you plug in x equals xk and compute the first derivative on the right-hand side, you're going to get f prime xk. If you compute the second derivative, you're going to get f double prime xk, right? Because the second derivative, these two go away. And the second derivative, this 2 cancels out the half. This disappears. You're going to be left with f prime xk, and so on. That's your standard Taylor series approximation. I'm sure you've done, or guys have done this in school, right? And so this should ring a bell. Does it ring a bell? Yes. Right, okay. Now if I use this Taylor series approximation for f of xk, assuming f of xk is my quadratic, how many terms do I need to take? Do I need a third term? Because this is quadratic. I don't need cubic and higher order terms, right? If I use this approximation, or this version of it, this is basically a Taylor expansion around some xk. Then if I try to minimize this, where is the minimum? Can someone tell me? Where's the minimum of this guy? How would you get this? How would you compute the minimum? Equate it to 0? What would you equate to 0? The derivative, right? So what's the derivative of this term? What's the derivative of this function? This first term, this goes away. When I differentiate this with respect to x, this goes away, right? If I differentiate this with respect to x, I just get f prime x, right? If I differentiate this with respect to x, what do I get? The 2.5 cancel out, right? Plus f double prime of x at xk, right? Times x minus xk. That's all that will remain, right? And if I equate this to 0, dividing by f double prime of xk, it's f double prime of xk plus this is equal 0, right? And so x is going to be xk minus 1 over f double prime of xk times f prime of xk. Would you agree with this? All of you guys, right? Now, look at your gradient descent rule on top. What is the step size I would need to get to the optimum in a single step?
1 by f double.
This step size. If I use this step size, I'm going to get to the optimum in a single step, right? There's a formula to it. Everybody good with this so far? Okay, so let's go back and just remember that for a quadratic function, of this kind, the optimum step size is 1 over f double prime of xk, regardless of where you are. If you take a step that's with that step size, you're going to get to the solution in a single step, right? So if I'm over here and I take a step with this step size, I'm going to get right here. What happens if my step size is less than 1 over f double prime? What will happen?
Take longer to converge.
It's going to take smaller steps, right? And so it's going to do this. Everyone with me? What if the step size is greater than 1 over f double prime? If it's greater, so this is eta is less than 1 over f double prime, right? If eta is greater than 1 over f double prime, it's going to do this. Is there a step size where it will not actually get to the bottom? Yes.
Suppose one where after you take the step, you end up higher than your original.
What is that step size? Yeah.
More than, like double distance, right?
Double. So what is that step size? 2f prime, right? If my step size were 2 times 2 over f double prime, I'm going to just keep bouncing back and forth, right? And if it's greater than this, then if my step size is greater than 2 over f double prime, this is going to walk out of the minimum, optimum. This makes sense to everybody? Right. That's very nice. So this is basically what happens over here. The optimal step size, if I use the half AW square plus BW plus C, is A inverse. And so if you take the optimal step size, you get to the minimum in 1 step. If it's less, you're going to take many steps, right? If it's greater, if it's so long as it's less than twice the optimal step size, you will bounce around and still get to the minimum. If it's greater, you're going to get the walk out of the optimum, right? Everybody with me so far? Yeah.
So here, I understand with the given step size and the learning rate, right? With the given step size and the f prime of x. If f prime of x was changing, but the step size remained the same.
This is independent of where you are, right? So long as I use my gradient descent rule, this is going to get, regardless of what xk is, if so long as I use the step size, I'm going to get to the optimum in a single step. It doesn't matter where you are. Okay, so this is for a scalar function of a scalar variable. Now, what's a function of a multivariate input? So if you have a function of a multivariate input, by the way, so even if your function is not quadratic, I can take a Taylor series approximation, truncate it after 2 terms, and if your step size is less than, twice the inverse of the second derivative at the current point, you can sort of hope to get to the solution in converge to the solution, right? But then let's go to multivariate functions, where the input has many dimensions. In that case, W is a vector, and so the quadratic is going to be half of W transpose AW plus BW, B transpose W plus C. Now, just for convenience, I'm going to assume that A is a diagonal matrix. The whole math works even if A is not a diagonal by just rotating the space to align up with the eigenvectors of A, okay? Or the same. Now, if I do this, then let's say I have 2 variables, x and y, and so actually, yeah, I'm going to say y equals f of x1, x2. So it's 2 variables, x1 and x2. And because it's quadratic, it's going to be half a1 x1 square plus b1 x1. So this is the contribution of the first term, plus half a2 x2 squared plus b2 x2. This is the quadratic contribution of the second variable plus c. This making sense? Right? Now, so this is a variable of a function of 2 variables. What will this look like? Assuming a1 and a2 are positive. It's going to be a bowl, right? And specifically because these 2 guys, there's no x1, x2 term in my example, right? So if I were to draw equal value contours for this function, there's some minimum, and it's going to be, if I just draw the level sets, if I slice the bowl at different heights, the edges are all going to be ellipses at different heights. Is this making sense to everybody? Okay. Now, when I use the gradient descent rule, what is the gradient descent rule? I'm saying xk, where x is x1, x2. So yeah, I'll just put a superscript here, just to make sure you don't confuse the two, equals xk minus 1 minus eta times, the derivative, right, of y with respect to, so this is the gradient, right, gradient of y with respect to x at xk minus 1. This is your gradient descent rule. So this is basically using the same step size eta for every component of the input, right? So are you guys with me so far? We are going to look at what happens because of this. Now, let's say I have a function of two variables. And so again, remember the constant a, 1 over a is your optimal step size, right? So let's say I have a quadratic function of two variables, and this looks like this. So this is a bowl. It's very steep in the horizontal direction. It's shallow in the vertical direction, right? So if you want to get to the optimum, you want to get here. Let me draw this dotted line. And let's say your current estimate is out here. Okay? Then if you want to get to the optimum in a single step, what is the step size you want to take? You want to take this step in this direction, but you want to take this step in this direction. Correct? Those are the optimal steps. Now, if you took an optimal step, if you did that, then you're going to end up over here in a single step. That making sense to everybody? But then observe that the optimal step size is different in the two directions, because the curvature is different in the two directions, right? And so, yeah, those are my pictures. I'll skip what's on the slides. The slides are pretty explanatory, but let's just go through my example, right? Suppose I took an optimal step size for here. Then how would the solution behave? If I take this as my optimal step size, is it going to converge in the vertical direction? No. So how will the solution behave? So in one step, it's going to go here, and then it's going to slowly come down, right? Suppose I take that can be really slow because in the vertical direction. Suppose I take an optimal step size for the vertical direction, then what will happen? Anybody? Yeah.
I think like the very worst case like ends up being greater than like the inverse of the outside.
If I take that's right. So if I take an optimal step size in the vertical direction, I'm also going to be taking the same step size in this direction, right? And so I'm going to end up here, and then in the vertical direction, I'm already at the optimum. I'm going to actually diverge in the horizontal direction. That makes sense to everybody? Right. So why is this happening?
We're using the same step size for both inputs.
We are using the same step size for every component, but the optimal step sizes are different for different components, although the function is still a quadratic, right? So I have some examples over here. Here's an example of a function of two variables. The optimal step size in the vertical direction is 1. The optimal step size in the horizontal direction is 0.33. So if I take a step size which is just slightly greater than 0.66, in the horizontal direction it's going to diverge, but in the vertical direction it's actually going to converge, right? So although the step size is good for the vertical direction, on the horizontal direction it's going to diverge, right? On the other hand, if I take a step size which is good enough for the horizontal direction, it's going to take forever to converge in the vertical direction. Does this make sense to everybody? And so you have this problem, right? The problem is that you want the learning rate to be lower than twice the smallest optimal learning rate for any direction. But that number can be very small for other directions. That makes sense to everybody, right? And so, but then, this is going to make convergence very slow in other directions. What is the ideal situation?
We have two different.
So the ideal situation is where all of the curvature in every direction is the same. The objective function is a perfect bowl. But you don't get ideal situations in real life, right? And so what we will find is, and this is also true for I just showed a quadratic. If you have non-quadratic functions, you can still take Taylor series approximations of these quadratic functions and the same behavior holds. So here's the thing. Convergence behavior becomes increasingly unpredictable as dimensions increase. for the fastest convergence, the learning rate must be close to both the optimal rate for the shallowest curvature and also for the steepest curvature. This means that ideally, the curvatures in all the directions must be very close to one another. So for any objective function, you can define something that's a condition number. A condition number is the ratio of the largest a to the smallest a. Remember, a is the constant for the quadratic, right? And if that ratio is large, then you have a really ugly function. Because if you follow the optimal step size for the steepest direction, then you're not going to converge in other directions. If you take as an optimal step size for something, one of the other directions, you're going to diverge in some directions. So you want this condition number to be as close to 1 as possible. But in real life, is that going to happen? You have no control on how functions behave. And so this is the problem you're going to have with neural networks, in the sense that, the actual objective function, although it's not a quadratic, you can think of it as being a bowl-shaped locally in the vicinity of every local minimum. And in that region, the different directions have very different curvatures. If you cater to one, you're going to blow up in the other. If you cater to the other, you're going to be very slow in the first. And so convergence is going to be tremendously problematic. So how would you solve for this? Yeah?
Possible to have two different learning rates?
Thank you, right? You want to decouple the learning rates for the different directions. But then how do you know what the optimal learning rate is for any direction? We don't really, because we have to analyze the function, right? But then, much of the analysis we saw was trying to ensure that the step size was not so large as to cause a divergence in a convex region. You don't want to go up. But is this necessarily a bad thing if it diverges?
Not as long as you're changing the learning rate. Not as long as you're changing the learning rate.
If I'm not changing the learning rate, let's say I keep it fixed, right? Or I'm allowed to change the learning rate, but is divergence always a bad thing? Yeah.
Maybe sometimes maybe the divergence is like it can prevent you from studying.
That's absolutely right, right? So let's say I have an objective function, which is like so. That's my objective function. And through some misfortune, my initial point guess is out here. And if I manipulate my learning algorithm so that it always converges to the local optimum, where am I going to end up? Where will I end up in this case? Anybody? Right here. Is that where I want to be? So how could I make sure that I don't get stuck there? Speak up, please.
Increase step size.
Increase the learning rate, and then what happens?
Then you would bounce around in the small area and eventually lead to the big one.
But if I do that, will I ever converge?
If it's not too big, I guess.
But then you can't really predict the behavior, right? So for complex models like neural networks, the loss function is not convex, right? So having a learning rate that's more than twice the optimal step size can initially get you out of any local minima that you happen to be in. But then if you stay with a learning rate that's greater than twice the optimal step size, are you ever going to converge? No, right? And so then you have this converse problem. So how do you resolve both? Yes?
You have, you drop learning rate and you so you find like a more comfortable curve to start with and then go down with longer.
So, exactly. So here's a principle, here's a general assumption we make, that the good minima, including the global minimum, tend to be in big bowls. Your function is almost never going to be of this kind where you have this and then you have this, where there's this one little guy, which is a global minimum. In fact, if you have an objective function, a loss function of this kind, this is probably not where you want to be. It's too narrow, right? It's going to be more like this, meaning your global minima, your good minima are in big bowls, and the local minima are in small bowls. And so you want to have a large learning rate initially, which lets you get out of local minima, and then slowly decrease the learning rate. And if you do that, eventually you're going to find yourself in a big bowl, and then you're going to walk down the big bowl, and the odds that you will actually hit a good minimum are much, much higher. And so this is basically what we do, right? Start with a large learning rate. If all of the directions are normalized, then it's learning rate greater than 2 times the steepest curvature, inverse of the steepest curvature, right? And then gradually reduce it with iterations. And so we have various rules for how this learning rate can be, the step size can be reduced, inverse of the iteration number or the epoch number, or you can have quadratic, proportional to 1 over k squared, k plus 1, because if k is 0, you don't want things to blow up, right? Or things that fall off exponentially, and various other strategies. Now, it turns out that this is really, really important when we begin talking about stochastic gradient descent, which we'll address in the next class. So here's a common approach. You train with a fixed large learning rate until your loss converges. Then you decrease the learning rate, and then keep doing this until the whole objective function kind of saturates. Questions? Yes?
Is it possible that the divergence could cause you to get stuck at another minima instead of the global minima?
It's very likely, but the point is you certainly don't want to be stuck where you currently are in most cases, right? So the thing is that if you have a large bowl of this kind, even if you're divergent, so long as you keep decreasing the learning rate, maybe initially you go up, but then your learning rate begins to shrink, and then you're going to go back down. Make sense? Yeah. The whole business of decreasing the learning rate with iterations means that if you find yourself in a big bowl, eventually you're going to get to the minimum. Whereas if you're in small bowls, you're going to get out. And small bowls are typically local minima, yeah.
Is there a way to estimate this beta optimum so that you can start with a large enough learning rate?
You would have to compute the Hessian, you would have to compute the eigenvector values of the Hessian, then find the smallest eigenvalue, twice the inverse. It's very complicated because for something as large as a neural network, computing the Hessian is just not feasible. Yeah.
What do we assume just like 2.001 in the homework? Like, do an analysis and it works.
You could, but do you really want to be doing that as part of your homework?
No.
Thank you, right? So the point is we've done a lot of the work for you. But the reality of it is you don't know what a good starting point is. There's a lot of magic to it. And so people have been working on this problem for years, and we just come and use some reasonable values. Yes.
So are the two facets that we want different learning rates for different parameters, but we also want to have it's okay if the learning rate is big at first because we want to climb out of suboptimal local minima, but eventually we want to get smaller so it can converge.
That's basically it, right? Eventually you're going to find yourself in a big bowl, at which point you want the learning rate. You don't want to keep walking out of bowls all the time. If the bowl is big enough, you want to get to the bottom, right? Questions? No? Okay, there's a poll. Yeah. There was one question. Where? Someone had a raised hand, yes. So at some level, you're going to be trying different learning rates. It's empirical. But then there are many things that we will be looking at in this class and the next, which actually deal with how you can sort of adapt your learning rate. Okay, guys. This was an easy one. So I'm going to ask, where are my glasses? So who's Typhlosion? Typhlosion. Who's Typhlosion? Typhlosion is absent, okay?
Oh, no, I was going to help you pronounce.
Okay, how do you pronounce that?
Typhlosion.
Typhlosion. Who's Typhlosion? Thank you, Jeffrey. And so, okay. Miss Drivers, is that the correct pronunciation? So who's Miss Drivers?
I'm Miss Davis.
Okay, Miss Rivers, can you mark the true statements here?
Just the first one.
All right. Step sizes that are greater than twice the inverse of the second derivative can cause it to diverge, but it's not always a bad thing because And also, gradient descent can converge with how decaying learning rates. What was an example we saw? The quadratic, you can get there in a single step, right? There's nothing decaying about it. So in a quadratic, so long as you're less than twice the optimal learning rate, you will always get to the optimum. So divergence causing learning rates may not be a bad thing. Decaying learning rates provide a good compromise between escaping poor local minima and convergence. But then many of the convergence ratios we saw arise because we have different learning rates for we have the same learning rate for every component. But if you have different learning rates for different components, are you really performing gradient descent anymore? Yes or no? A gradient descent means you're walking in the direction opposite the gradient, right? Which means you're taking this a step size proportional to the partial derivative in every direction, and the proportionality constant is the same in every direction. If you begin changing the learning rates for the different components, then you're no longer walking in the direction of the gradient, you're walking in a different direction. And this is the challenge. Once I begin walking in a direction that's different from the gradient, then all of the nice assurances you have with gradient descent that you're going down, those go away. And that's something you're going to have to deal with. Does that make sense to everybody? Right? And so figuring out what is an optimal step size for every direction ends up being a challenge. Now, so the problems arise because of requiring a fixed step size across all dimensions, because step size is tied to the gradient. Let's try releasing this requirement nonetheless. And there have been very many approaches proposed to release this requirement, where you look at each direction independently. The two earliest ones were RProp, resilient propagation, and QuickProp. QuickProp is still very, very popular. And these are nice algorithms that you can find in PyTorch. QuickProp was invented by our own Scott Fahlman and CMU. And they sort of take a different, they optimize along each direction independently. I'm going to talk only about RProp. QuickProp is on the slides, okay? So how does RProp work, resilient propagation? It's a simple algorithm that you follow independently for each component. So every single weight is going to be doing this independently. At each time, okay, let me do this with a picture, right? So let's say this is your current, W hat 0 is your current estimate. At that point, the derivative is negative. Do you want to move right or left? Right or left, guys?
Right.
Okay, thank you, right? So I move a step right. And so I take a step here. I find the derivative is still negative. Am I going in the right direction or the wrong direction?
Right.
So this means, should I decrease my step size or increase it? I'm going the right way. So what I will do is, if I have an initial step size of, say, delta W0, I find I'm going in the right direction, then I'm going to do maybe 1.1 times delta W0. I increase my step size. I do this, I find I'm still going in the right direction because the derivative is still negative. So then I'm going to multiply my current step size again by alpha, say 1.1, and take an even larger step. I'm doing this independently, component by component, right? Eventually, you get to a point where my step size is so large that I've gone on to the other side of the minimum. How would I find out that I've gone to the other side of the minimum? So the derivative would go from being negative to being positive, right? The sign of the derivative would have changed. If I find the sign of the derivative has changed, then what would you do as a heuristic? I am going to go back, I took too large a step, and I'm going to take a smaller step forward, right? So I can just go back, and then I'm going to scale my step size down by some beta, and then take a smaller step forward. That making sense? Yes, Jeffrey?
So basically, you do a do-over of the step where you switch signs?
So I'm not sure I understood.
A do-over means that
That's right. You do it. Yeah. So you want to do a do-over. That's correct, right? You seem to be falling asleep. You need to go take a break for coffee?
No.
Okay. Sorry. If you want to go wash your face, that's fine. So this makes sense to everybody? you can now, where does gradient descent or where does backpropagation turn up in this algorithm? Anybody? Yes? You need backpropagation to find the derivative, right? If you don't know the derivative, you don't know the sign of the derivative. And so here's the overall algorithm, this is the overall algorithm for here. I'll just leave it on the slides. Typically, you keep increasing your steps, but there's a ceiling. Beyond a point, you don't take the step, make the step larger. If you overshot, you keep decreasing your steps, but then there's a floor. You don't make it smaller than something. And at each point, you need to know the sign of the derivative, for which you need the derivative, which can be computed using backpropagation, right? So these derivative terms are computed using backpropagation. Again, note that this is being done independently for every parameter. So you'll be storing a lot of information about the derivatives and the previous derivative for every parameter, just so that you know whether they're going in the right direction or not. And that's how you adapt your step size independently for each parameter. Like I said, if I'm breaking the rules of gradient descent, then I have no way of knowing what I am doing. Having a different step size for each parameter sort of breaks any guarantee that I'm actually going to be going in the direction of decreasing loss. So I have to keep track of different things for each parameter independently. Yes, Ankit?
Wouldn't this mean that you get stuck in local minima more frequently?
Yeah, it turns out that you don't actually. So it kind of works, yeah.
So as if you're updating each parameter independently.
Yes.
If like initially your derivative was like positive, would derivative basically tell you to move left while you keep increasing your step size until it switches to negative, upon which
That's right. So if your derivative is positive, you take a step back, then you check the derivative, it's still positive, you take a larger step back. You keep doing this till the derivative is now negative, then you go back and redo, right? Yes.
But even if you reach the optimum for one of the parameters, you still compute all of it. Like you still try to update it, but you make smaller and smaller changes.
That's basically what you would be doing, right? If the derivative, you rarely get to zero derivatives, so, but yeah.
I'm wondering if every time that your derivative changes, you decrease the learning rate, how are you going to get out of the local minimum?
So this is being done independently for every step, right? So let's say you're here. You took this step. So now you took a step this large, and then you scaled up the step size, and then you ended up here. So then you found that you walked too large, taken too big a step. So then you go back here, and you decrease your step size. But then if you decrease your step size, you end up over here again. So then you go right back and do a do-over, but then you take an even smaller step size. If you keep shrinking it, eventually you're going to be taking a step size that doesn't overshoot, right? And so then you're back to square one. The previous step tells you how much you could have walked in the direction of the derivative, and then you can scale it up. Did that answer your question?
So wouldn't that make you stay in a local minimum instead of go out of it?
That is true, right? This is going to get stuck in local minima, but it just turns out that, typically, when you hit a local minimum of this kind, so their objective functions tend to have a specific characteristic. If you have local minima, they tend to be very local, so you maybe have something like this. And so when you overshoot, more often than not, you're going to skip those guys. Yeah. Any other questions? Yeah.
You mentioned earlier that one of the optimal step sizes would be taking the eigenvalues of the Hessian and then using the inverse.
Yeah.
If we can't compute the Hessian, why not use power iteration or like cells or something and then just approximate those?
Take a look at quick prop. So the way you do it is you look at the derivative of the current step, you take the derivative of the second step. The difference of derivatives gives you some approximation to the second derivative. So that's what quick prop does. Right. So it's a remarkable first order algorithm that's frequently much more efficient than gradient descent and can be competitive against some of the advanced second order methods and some of the methods that we'll see in the next class. And only makes minimal assumptions about the loss function. You're not even assuming convexity, right? You could have a function of this kind and you're still going to get to the minimum. So gradient descent naturally assumes convexity. This does not. Here's a Jeffrey, I need your help. How do you pronounce Cyndaquil?
What's CY? Oh, Cyndaquil.
Cyndaquil, okay. Who is Cyndaquil? Cyndaquil is absent.
Here.
Okay, all right. What's the answer to this question?
I think it's the first one.
Right? So if the derivative is currently positive and after taking a step it becomes negative, it means you've been walking backward, you've overshot. So then you're going to go back to the earliest position and then take a smaller step. Make sense to everybody? Right, easy one, right? And so quick prop is a similar technique where, except that in quick prop you actually come up with an approximation to the second derivative as a difference in derivatives at consequent steps. And so it employs Newton updates with empirically derived second derivatives, and it's prone to instability for non-convex objective functions. But quick prop, which we won't be looking at in the class, but it's in the slides, is still one of the best, optimal, best trading algorithms around. So gradient descent can miss obvious answers. That's the first thing we saw, right? But this is a good thing because it reduces variance. Vanilla gradient descent may be too slow or unstable due to the differences between the dimensions. You can have second order methods, which, if I have a bowl which is steep in one direction and shallow in the other, then I can normalize the different directions to make the bowl more circular. And that's what second order methods do. You sort of scale the various dimensions so that the objective function becomes more bowl-like, symmetric, isotropic, and then you can have the same step size in every direction. Adaptive or decaying learning rates can improve convergence and can also help you escape local minima. And methods that decouple the dimensions can improve convergence, right? Questions? Okay, yeah.
If you start the R-prop algorithm initially and your derivative is positive, then because you have no prior state to default to, what does it do in that case?
So in the first step, that's your initialization. At the beginning, you're going to have some step size. That's the only hyperparameter you're left with. Right? So now here's another closer look at the convergence problem. If I have dimension-independent learning rates, the same learning rate in every dimension, let's look at it a little more formally. What are the things I can do? So we had these examples where I was converging cleanly along the vertical direction, but in the horizontal direction, I was bouncing around. What is a clear difference between the two behaviors? In one direction, the steps were always in the same direction, right? Whereas in the direction in which I was getting unstable, I kept changing direction. So can I use this somehow to figure out that in the horizontal direction, I'm walking too much, my steps are too large. And in the vertical directions, my steps are small enough, right? I should be able to use this information, right? The way we will do it is using, keep track of oscillations, emphasize steps in directions where you're walking in the correct directions, the derivative doesn't keep changing sign, and then shrink the steps in directions that bounce around. So this makes sense, right, intuitively. And that leads us to momentum methods. What we will do is maintain a running average of the gradients. So if I'm maintaining a running average of the gradients, you're maintaining a running average of the derivatives in every direction. The nice thing about the running average is that if you look over here, in the vertical direction, the derivative is always pointing, the negative of the derivative is always pointing down. So the running average is going to continue pointing down, and it's going to be long. In the horizontal direction, it keeps flipping. So what will happen to the running average? The positives and the negatives are going to keep canceling out. It's going to become smaller and smaller. It's going to become somewhat zero, right? They cancel out. So that's what we will do in momentum methods. In directions in which the convergence is smooth, the average will have a large value. In directions where the estimate swings around, the positive and negative swings will cancel out. And you're going to update using the running average rather than the basic derivative itself. And so here's what we do. If you're doing a plain gradient descent, you're always taking a step orthogonal to the level set. And so that would be the gradient descent for the figure on, the figure on the left. But then if I'm maintaining a running average of derivatives, I'm going to have a solution like the one to the right. So how do I do a running average of derivatives, of steps? So again, remember the step is the negative of the gradient, right? So if I have, at any point, let's say I have, I'll just call that here, W. This is my current derivative. So the gradient is going to be the negative of that. There's a step size eta that I can use, right? So now if I've taken a step so far, and let's say my current step is delta W. My current step is the integral running average, is based on the running average of all the derivatives I've had so far, right? So for the next time around, instead of using the same guy, I'm going to scale this down by some alpha and then some beta times the current step size, which is minus eta. This is what the gradient by itself is going to suggest to me. But then I'm scaling it and then adding it to what I've done so far. And so that's what I will have. The gradient step is going to be minus eta times the derivative. And I'm going to add that to a scaled version of what I've done already. This is my running average. And the actual update is going to be performed using the running average. This is making sense to everybody? And it turns out that if you do this, you actually end up with arriving at the optimum much faster, right? So I have a pseudocode for this. You're still going to be using backprop to compute the derivatives, but you're not using the derivatives directly. You're using a running average of the derivatives. And the nice thing with this is that when I'm performing a running average, the running average derivative will naturally scale up the consistent directions and scale down the inconsistent directions. And so I have factored in, as a result, this is the equivalent of having non-uniform learning rates in every direction, because I'm scaling up some dimensions and the steps in some dimensions and scaling down the steps in other dimensions. So this works. But then I can do something even better, right? So here's what the momentum rule does. At any point, I say the previous step was shown by the red line, right? Then I would compute the derivative, and the negative derivative is going to be given by this blue line. To this, I add a scaled version of the step I took at the last step, in the last iteration, and that's going to give me my new step, right? The next time around, at this point, again, I'd be computing a derivative and taking a step against it, adding some scaled version of the green line, and that's going to give me the next step. But then observe what I did over here. I took a step, then I walked against the gradient, and then I added a scaled version of the previous step. So I just went up the green line. So I went to that first dot, computed the gradient. That told me to go up the green line. And then I added a scaled version of the previous step, which is the second red line, and that got me to the new point. It turns out I can change the order. So what I can do instead is I can first take a step which is a scaled version of the previous step, and then compute the gradient at the new point, and that's going to give me my new step. So this is still the momentum method, except that I've changed the order. Instead of taking a gradient here and then adding in a scaled version of the previous step, I just take a scaled version of the previous step, and then I walk against the gradient. And so this is Nesterov's accelerated gradient. It turns out it's optimal. It's much better than basic. The first method is called the momentum method. This is even better. And for convex functions, it's optimal in many ways. I tried reading the paper a long time ago, and the first line in the paper said obviously, and made a mathematical statement. And then there were a few pages of math after that. So I took this first line to my PhD student who had won a gold medal at the International Math Olympiad. And he worked on it for like 6 hours and then came back and explained why it was obvious. So I don't really understand this. But anyway, this is how it works. And so that's Nesterov's method, right? You take a step. So from the previous position, you take a step which is a scaled version of the previous step. And then you compute the gradient. And that's going to take you to the new position, right? That's Nesterov's accelerated method gradient. We're going to see more of this in the next class, right? So here is a comparison of momentum with gradient descent. This is from Hinton. The blue line is the momentum method. Gradient descent is bad. The blue line is the momentum method. And the green line is Nesterov's accelerated gradient and gets to the solution in 2 steps. So pseudocode for it. Anyway, momentum and trend-based methods, we quickly also glance through this. We're going to revisit this. We're going to one last poll. I keep misplacing my glasses. So pardon the slight. So who is Kingler? Is Kingler around?
Oh, Kingler.
Yes, I am here.
What is the answer?
It's true.
It's true. So it's false, right? Because if you have a flat slope of surface of constant slope, the running average of the derivatives is no different from the basic derivative itself. And so the two of them, gradient descent and momentum, are going to walk at the same rate. Okay? Thank you, guys. Just to quickly wrap up, gradient descent can miss obvious answers. Vanilla gradient descent may be too slow, etc., etc. What we added today in the last few minutes is that momentum methods which emphasize directions of steady improvement are demonstrably superior to other methods. We will be talking about incremental updates. We'll revisit trend algorithms and some tricks of the trade in the next class. Thank you.